We now try a couple of practice problems. The first, problem 3105, involves a channel AB that is fixed in space. The plane containing edges AC and AD of the channel is parallel to the XZ plane. If the surfaces of the channel are frictionless and the sphere E has a 2 kilogram mass, we want to determine the forces supported by chord EF and the reactions RC and RD between the sphere and sides C and D respectively. Take a moment now to pause this video and resume playing when you are ready to see a solution. Our attention here is naturally drawn to the sphere, so I'm going to draw an isolating surface around that as the basis of a free body diagram. We have the weight of the sphere, which we know, and I'll represent that as minus the scalar value of the weight in the I direction. We're cutting through the cable EF, so we'll represent that as a tension EF with a scalar magnitude that we're trying to determine on a unit vector in the EF direction that we can get from the information in the figure. How should we represent the reaction forces provided by the edges AC and AD of the channel? We're told that the channel surface is frictionless, which tells us the reaction force is purely normal to that plane. We'll talk about how to find those normals in just a minute. For now, we'll represent those forces this way. On the left-hand side, we'll write the reaction at D is a magnitude we're trying to determine with the unit vector normal to the left surface of the channel. And on the right, we'll have a reaction C with an unknown magnitude on another unit vector normal to the channel on the right-hand side. So how should we define these unit vectors? For EF, we have a unit vector that lies in the XY plane, and we can see this 20-degree angle that's defined off the vertical axis, which is the x-axis. And knowing that the unit vector will just have components cosine theta and sine theta, where theta is a relevant angle, we can see from the figure that that unit vector will be cosine of 20 degrees in I, and then minus sine 20 degrees in J, because it's going backward along the y-axis from E to F. Now, how should we define these unit vectors UC and UD? We could see from the figure that we could define two unit vectors along AC and along AB. And then, since the normal reaction force will be perpendicular to that plane, we could generate a new vector by taking the cross product. So let's first note that a unit vector from A to C, sine 30 degrees in I, and plus cosine 30 degrees in K. We might also note that UAB is sine 30 degrees in I and minus cosine 30 degrees in J. Note that if we take a cross product between that unit vector along AC and that along AB, sweeping AC towards AD will give us a unit vector that points up and out in this direction. That will give us a vector that's aligned with the unit vector UC. We might also note that taking the cross product of UAC with UAB will not generate itself a unit vector. We'll have to divide by the magnitude of that cross product to make it so. We might also note that to get the proper orientation for U sub D, we're going to need to take the cross product between UDA and UAB. That cross will again give us a unit vector that points in the correct direction to make a unit vector consistent with UD. So we'll note as well that UDA is minus sine 30 degrees in I plus cosine 30 degrees in K. So let's first generate the unit vector U sub C. That's going to be equal to UAC cross UAB over the magnitude of that cross. And again, we have to divide by that magnitude because UAC and UAB are not perpendicular to each other, so the sine of the angle between them is less than 1. The components of our cross product in the middle row will be sine of 30 degrees, 0, cosine 30 degrees, and the bottom row for UAB will be sine 30 minus cosine 30, 0. And using our cross product rules in the I direction, we'll get 0 minus a minus cosine squared 30, so that will give us cosine squared 30 degrees in I. Then we'll have a minus j times a 0 minus a product of sine 30 and cosine 30, which will give us a plus sine 30 degrees cosine 30 degrees. And in the k direction, we'll have a minus sine 30 cosine 30 minus 0. This gives us values of 3/4 I plus root 3 over 4j minus root 3 over 4k. Taking the square root of the sum of the squares to get the magnitude of that cross, we find that this is equal to root 15 over 4, and so our unit vector UC ends up being 3 over root 15I plus root 3 over root 15j minus root 3 over root 15k. We could carry out the same operations to get the unit vector d on the left-hand side. We would get that from UDA cross UAB over that magnitude. And I won't carry through those details here, but it's going to look very similar to the result we got for UC. Here the only thing that changes are one of the components, that being in the k direction. So this ends up being 3 over root 15I plus root 3 over root 15j, and now plus root 3 over root 15k. Having now found all these orientations, we're prepared to write the scalar components of our force equilibrium equation, and in the I direction we'll get TEF cosine 20 plus 3 over root 15 RC plus 3 over root 15 RD minus the weight of the sphere equals 0. We'll call that equation 1. In the y direction, we have minus TEF sine 20 plus root 3 over root 15 RC plus root 3 over root 15 RD equals 0, and we'll call that equation 2. And then finally, in the z direction, we simply have minus root 3 over root 15 RC plus root 3 over root 15 RD equals 0. Call that equation 3. And that last equation is telling us that we have the same reaction magnitude on either side of this channel, and that's not surprising. The figure is given from a perspective view, but everything about that is going to be symmetric about the xy plane, and so it's not surprising that RC and RD would be the same values. We'll substitute those results into equation 2, from which we'll get RC is equal to RD is equal to TEF sine 20 times root 15 over 2 root 3. We'll then take this result and put it into the first equation, which we can write as TEF times the quantity cosine 20 degrees plus 6 over root 15 times root 15 over 2 root 3 sine 20 degrees equals the weight of the sphere. And we have some things that will cancel out here. In fact, the number preceding sine 20 degrees will just be the square root of 3, and we end up with TEF equals the weight of the sphere over the sum of cosine 20 degrees plus root 3 sine 20 degrees. And if we put in for the weight of the sphere 2 kilograms times 9.81 meters per second squared, we end up with a value for the tension in EF of 12.81 newtons. If we then take those values and substitute it back into our expression for the reactions at C and D, we get a value equal to 4.897 newtons.